Hello all, it's video number 3 for section 1.1, the last video for 1.1. We're just going to go over another example. So in this example, we're going to determine whether or not the following linear system is consistent. So recall, consistent just means we want to know if it has a solution or not. We don't even need to find the solution. I mean, of course, that's practically what you do every time anyways. If you want to determine whether or not there is a solution, you try and find one, and we'll see. Okay, so then here we have our linear system. We could do all this in terms of the equations, and you'd be carrying around a bunch of extra notation. So the first thing we're always going to do is start with the augmented matrix and apply our row operations. So here we have our augmented matrix, where we just record all the numbers present. So 2, -2, 12, -2, 2, -1, 10, and 1, 1, 1, 2, and 6. Okay, and then so the trick is always try to eliminate, you start with x1, try to eliminate other occurrences of x1 in the other equations. So maybe to make our life simpler, we can start with this first row, and divide everything by 2, since we see there's a common factor of 2 there. And we know that multiplying or dividing by non-zero constants is a perfectly acceptable row operation. So let's do that. Let's replace row 1 by a half of row 1. And so our new matrix is then 1, -1, 6, -1, and then the other 2 rows haven't changed at all. 1, 1, 2, 6. Okay, and now what we're going to do is use the one we have in this first row, first column to eliminate everything else in that column. So if we want to eliminate the 2 in column 1, row 2, we had better take row 2 and subtract 2 times row 1. So we'll take row 2 and we'll alter it to row 2 minus twice row 1. Okay, so row 1 hasn't changed, and now we've got 2 minus 2 times 1, that's 0. We've got -1 minus 2 times -1, that's -3. Sorry, double check that. -1 minus 2 times -1 is -1 plus 2. Sorry, that's the positive one. There we go. And now we've got what? 10 minus 2 times 6 is 10 minus 12 is -2. And now 1 minus 2 times -2 is 3. Yeah. Oops. All right. And then our third row hasn't been changed at all. Okay. And we can do the same thing for row 3. Here we want to replace row 3 by row 3 minus row 1. So let's see how that goes. Row 1 hasn't changed. Our row 2 hasn't changed from the previous step, and now we've got 1 minus 1 is 0. We've got 1 minus -1, which is 2. We've got 2 minus 6 is -4. And we've got 6 minus -1 is 7. Okay, so we've succeeded in eliminating everything else in this column. Now we should choose a new candidate for our x2 and use that to eliminate everything else in the column. So let's take this 1 in our second row, second column, and use it to eliminate the -1 and the 2 there. And if we're getting tired, maybe we can do 2 row operations in one step. So maybe let's replace, what do we want to do? We want to replace row 1 with row 1 plus row 2, and that that the -1 is going to become a 0. So row 1 goes to row 1 plus row 2. And at the same time, let's do row 3 goes to row 3, minus 2 row 2. Okay, so let's see how this is going to go. Our row 1 does change. We've got 1 plus 0, so that's still 1. We've got -1 plus 1, that's 0. We've got 6 plus -2 is 4. We've got -1 plus 3 is 2. Our row 2 isn't changing at all. It's hanging out. And then our row 3 is going to change as well. We've got 0 minus 2 times 0, that's 0. We've got 2 minus 2 times 1, that's 0, as by design. We've got, now I've got to be careful, we've got real arithmetic. We've got what? -4 minus 2 times -2. I gotta write this out for a second, otherwise I'll make a mistake. We've got -4 minus 2 times -2. So this is +4. Okay, so it's equal to 0. I can't do everything in my head, folks. And next we've got 7 minus 2 times 3 is 7 minus 6. So that's 1. Okay. And since I'm such a pro, here I'll erase there we go. Since I'm such a pro, something occurs to me. So we should look at this and stare at it for a second and think, what is the corresponding linear system? Because these are just numbers in some array. We know that they're supposed to represent systems of equations. And so when we go back and look at the system of equation, something should pop out at you. So let's see what happens. So let's consider the linear system this represents. Linear system. This represents. It represents the linear system that says x1 plus no x2s plus 4x3 is equal to 2. We've got x2 minus 2 times x3 is equal to 3. And this last one is just that 1 is equal to 0. That should get that should bother you. If that doesn't bother you at all, you've got to talk to somebody. It should be physically painful to write down 1 is equal to 0. You got to put on a happy face around that. This means our system has no solutions. There's no way, there's no value of x1 and x2 that you can make to make this thing acceptable. Never acceptable. Always a bad time. So whatever we've done, we've showed that, we've arrived at a linear system that has no solution. So let me put that in red and bold, no solution. And we've got there by operations that don't change the solution set to our linear system. So since there's no solution to this absolutely face-melting system, it means there can't have been a solution to the original one either. So since we used row operations to arrive at a linear system without a solution. So since we applied operations to our original linear system that didn't change the solution set, and the result of something without a solution, the original linear system can't have had a solution. Our original linear system has no solution. Which means it is inconsistent. Okay, and that was the purpose of this problem. So often, moving on, there'll be sort of two main questions that we focus on, or that'll keep on coming up in this class, and that is, does a solution exist? And if so, is it unique? So in this case, there's no solution, so we can't even ask the second question. But existence and uniqueness is going to come up over and over in linear algebra. It'll come up over and over in differential equations as well for a related purpose. Okay. Take care, everybody.